Third is performance analysis. What is the running time of this algorithm? What is the space complexity of this algorithm, and so on and so forth. Performance analysis. And we sort of observed that for divide and conquer technique, the most non-trivial or intellectually challenging thing is to come up with the non-trivial come up with an algorithm itself. And typically, if you have come up with a correct algorithm, the correctness is very obvious. And performance analysis is also easy in the sense that all you need to do is typically solve or no or you need to solve a recurrence relation. On the other hand, for greedy, coming up with sort of algorithms is easy. Given a problem, what is the algorithm? It is typically easy, and typically non-trivial. And what makes the greedy algorithm interesting and non-trivial and buggy is this step proof of correctness. And on top of it, typically most greedy algorithms are incorrect. We saw for the for a concrete problem of scheduling jobs in a single machine, the first step is we thought of various possible algorithms, and we discovered that all of them except one is incorrect. All of them are incorrect, and that is the typical journey with greedy algorithms. And we have not done performance analysis. I just left it to you. It's typically very easy. So again, recall that in the last class we took this concrete example of scheduling jobs in one machine to minimize the sum of weighted completion times. We use this example to demonstrate the process of greedy algorithm design. And what was the algorithm? The algorithm that we found at the end is to sort the jobs in non-increasing or non-increasing order of Wi by Li. Yes, non-increasing order of Wi by Li, and perform the jobs in that order. And we proved that this technique indeed leads to correct solution, optimal solution always for all the inputs using an exchange argument. Today, our example is Huffman coding, and we will see that we will see an algorithm for it, and we will also see the proof of correctness. And this we will see that the proof of correctness is little more challenging, little more interesting than the yesterday's example of machine scheduling, job scheduling. And we'll see that this proof of correctness of Huffman coding involves actually two sort of techniques, which is exchange argument, the same exchange argument, the same tool that we used in our last class, and on top of that we will need induction. So this is the plan for today's class. Any question or till now before we define what is Huffman coding? Okay, very good. So what is Huffman coding? Here is the input. Input is a set sigma of a set of symbols sigma, which is called alphabet, and it has n symbols, and each symbol has a non-negative frequency Pa of each symbol. It's assume that it's like how frequent a symbol appears in a dictionary, or not dictionary, in a say in a novel, say Macbeth, and so on and so forth. Typically, what is the frequency? For example, the vowels appear much more often than a symbol like say J or say Z, something like that. So this information is given, and this information is often available from the data. And what is the job? The job is on a high level. The job is to find the encoding of these symbols into binary strings, binary codes, such that the encoded message is sort of sort of has minimum average length. That way, for example, if I want to store say a MACPath, and if I use a coding which uses a long code, a long binary string for representing say a vowel, say A or E, and uses a short code, short binary string for representing uh, a less frequent, a rare symbol like J or Z, then I am that coding is not so efficient, because there will be lots of vowels, and those symbols I am using long codes. So that way, encoded message won't be efficient to store. I need to use more space to send it over a communication channel. I need more bandwidth, and so on and so forth. Everything is inefficient here. So what I want is to minimize the average length of the code, and concretely what I mean is minimize sum over the symbols in the alphabet in sigma, the frequency PA. Frequency is the number of times, how many times the symbol appears, and times the number of bits used to encode the symbol A. Okay, so that is a job. Input is a set of symbols, and for each symbol I am given its frequency. The output is, for the time being, let's not focus on prefix free. We'll see what it is. For the time being, let's assume the output, we need to output a binary code of minimum average length. Question on what is the input of the problem, what is the output of the problem, what we are supposed to do.
Sir, can you give an example?
Yes, for example, suppose my sigma has, so this example has three symbols only, A, B and C. And suppose PA is say 2, PB is say 5, and say PC equal to 1. These are frequencies. This need not be, these are real numbers. This can be real numbers also. It, it can't be negative, that's it. It can be 0 also. And I need to find a coding. So what do you mean by coding? Coding is that I need to tell what is the binary string, because it is a binary coding. What is the binary string I will use to store each of these symbols? As you know, that computer is a binary machine. All it can store and operate is 0 and 1. I can't store A. To store A, I need to convert it to some representation which involves only 0 and 1. So maybe I decide that, okay, to store A, I will store 1 0, or say 0 0, the most obvious one that often comes to our mind. For B, whenever I need to store B, I will store 0 1. For C, I will store 1 1. Then what is my so let's call this say cost. So what is the cost for this coding? The cost will be PA appears, its frequency is 2, and the number of bits used to represent A is 2. PB appears, frequency is 5, and number of bits used is 2, and PC is 1, and the number of bits used is 2 again. So what is this? 816. So this is the cost of this particular encoding. The job of this problem is to find a mapping, this table, find this table, this encoding. Find this encoding, this blue table, which minimizes the sum of this cost. See, the average length of the encoding. Average length. Is the problem definition clear?
Yes, sir.
Okay. Now, can someone improve upon? Can someone give me another code which does better than this at least? Come on, very easy. Give me another code which does better than this. Just better than.
0, 0, 1, 0 and 1, 1.
Yes, very good. Thank you. What is the need to use two symbols for each code? You can use, for example, make it 0 and say keep this 0 1 and 1 1. What is the cost? Cost is now for PA it is 2 and others remain same. So what is it? I think it is 15, 14. Can someone give me an even better code?
0, 1 and 0, 1.
0 1 and 0 1. What is the use for say another extra things? I want to minimize the space. A, B, C. Maybe 0, 0 1 and he's saying 0 1 and 0 1.
But sir,
Okay.
then C will become same as AB.
Let's see. This is 1 times 2 plus 5 times 1 uh, plus 1 times 2. 4 9. Yeah, this is very good. But can someone point out a problem here except the except that that student who just spoke? You don't speak. Can someone else find out a problem with this code?
AB becomes C if AB and B are together.
Very good. The decoding is decoding is ambiguous. For example, obviously we want each string of over alphabet to map to different strings, so that while decoding the encoded string, there is no ambiguity. There for every encoded message, the encoded binary string, there should exist a unique message. But that's not the case here. For example, 0 1 is the encoding for both AB and C. So to avoid this problem, what property our code should satisfy, or coding scheme should satisfy? Can someone tell me what property should it satisfy? Of course, obvious properties from the definition, that the property is that there cannot be two different strings which leads to same code, binary code. But yeah, that's from the definition. Can someone give me?
No code should
Sir,
have
as we start like from the leftmost part of any encoding for a particular alphabet, we should not find another, like we should not encounter the coding of any other alphabet.
Very good. And the other student was also saying something like that only. Is that the case?
no code word should be prefix of some other
Very
code.
good. Prefix free code. The problem is that some part of the code, a code word, yes, code word is a better word. Code word of any symbol should not be a prefix of another code word. For example, the code word for A is a prefix of code word of C, and that's what the problem. And so, what is our goal? In Huffman coding, the goal is don't give me any code. Restrict your search for minimizing the average length only in prefix free code, because they are very easy to encode, of course, and of course decode. Okay, but I would just not leave you, give you a sort of puzzle. Is can you think of a or think of a non-prefix free code, but which satisfies the unique decoding property? Think of a. Can you give me an example? So here is a puzzle, or can there exist such a code? Let me pose a question. These are fun exercises. Or let me write, do there exist? Do there exist? Does there exist a non-prefix free code?
So
Yes.
a trivial example could be having a code which goes like 0, then 1 0, then 1 1 0, 1 1 1 0. So in that case, there can never be
Just a minute. Just let me finish the question. Does there exist a non-prefix free code? Have having unique decoding. Yes. So yeah, are you telling me an answer to this question?
Oh, sorry, sir. Sorry, sir. I was giving a prefix-free code. Sorry.
Correct. But you're right. He was giving an example of prefix-free code. So once the problem is understood, what is the first task in a greedy algorithm design paradigm? Think of various, think of various greedy algorithms, right? And then we'll see which one is correct, which one is not correct. So, so say possible algorithms. Possible algorithms. Why possible algorithms? Because I am just talking about approaches. Once I prove that some approach is correct, then only I can say it's an algorithm. So one possible algorithm that one of you just told is that you have n symbols, right? So let's call it say a1 to an. Why don't you do it this way? So 1, 0, 1, and so on. 0, 0, 0, 0. This is n minus 1, 1. This way it is prefix free. Of course, anyone has any doubt that this is a prefix free code? No code word is a prefix of another code word. Is it optimal? Is it always the best code word? Because the job is to minimize the average length of the code. Okay, we'll see. But how about some other approaches? Can someone suggest some approach, some other approaches? Typically, our our thinking is that for greedy algorithms, it should be easy to come up with many approaches.
So we can go like with 1, then 1 1 1 0. Then if you have 1 0 1 0 1 0, like can if you have like 4 or more or 3 or more, we can simply permute them.
So you're saying that no, don't do these variable things. Do the fixed length coding. Right? For example, just allocate say log n base 2 ceiling of log n base 2 base 2 code for every symbol. Is this your approach? Hello.
Not exactly like for example, instead of going 0 1, then again 3, then 4 digit, then 5 digit, we can whenever we are reaching 4 digits, we can permute them and we can still get unique codes.
I have not got it. Can you help me? So for A1, what should I write?
1.
1. Okay. For A2?
0 1 or 1 1 or anything within that.
Just let's for concreteness, what should I write? 0 1.
Yeah, 0.
Then A3?
We can go with 3 digits, 1 0 1 or
1 0
0
1.
1 0 1 1, something like that.
0 1 1. No, just for concreteness, 0 1 1. Whatever you'll say, I'll write. Then for
No,
A4?
no, sir. I think it's wrong. My approach is wrong now.
Okay. Okay. So let me erase this thing. But this is counterintuitive. Like, we're doing greedy algorithms, and the teacher told in the last class, coming up with greedy choices is easy, but here it is a bit difficult. Fixed length of definitely not the correct approach, because we have seen an example, namely this, where fixed length coding does not give the minimum average length. So we have only one thing. Is it correct or is it not correct? Either prove correctness or give me a counter example. You're all awake, right?
Yes, sir.
Yes, okay. I say this can't be correct. This is trivial. This can't be correct. Can someone tell me why it is trivial? It's clearly visible that it can't be correct.
So number one.
Number one. Yeah, number 2 and 3 we have already discarded. Number one, it can't
So
be
I
correct.
think in some cases it would be correct.
By correctness, I mean that it is correct. It gives the correct output for all possible inputs.
Sir?
Yes.
So do you mean
Sir,
like it
because
will?
some AIs are postfix also for another AI.
Postfix is not a problem. Prefix free is problem. What I am not correct by that I mean that it does not always output the smallest possible code. So, code with having smallest possible average length.
So in the second example that we took when we got 14 as the output, so isn't that a correct solution as well?
For this one, I don't know. It may be the correct solution, but the goal is not to. So this was started with an example. So are you asking whether this
Yes,
one a correct
so
solution
in
or
the
not?
second example, if we go by the solution that you are suggesting, then we'll have 0 for A and 0, 1 for B, and then 0, 0, 1 for C. So we'll get like a
Correct.
bigger answer.
Correct. Very good. Very good. Thank you. And there is no point. What is the point of this? Clearly not the thing, because every step we are increasing. You are adding one more bit. Is it needed? For example, n equal to 3, 1, 0, 1. You can use say 0, 0. You don't need 3. That's one. Second is it is not even looking at the frequencies, this algorithm. That also you can say that okay, then without loss of generality, sort the symbols in decreasing order of frequencies. That means A1 has highest frequency, but then as one of you just pointed out, that the second case is a counterexample.
So, but the second case is not a prefix free code. So how can we use it to?
Second one.
So
yes,
A
correct.
is a prefix of B. So we shouldn't compare the two.
Yes, correct. That's true. So second one is not the concrete, not a counterexample. So we are still finding whether first approach is the right approach or not. Yes, very good point. Second one is not prefix free code. Okay, so any counterexample or proof of correctness for the first approach? Assume that clearly that P1 is highest. Assume that there are no ties, if that helps you.
Sir, I have a counterexample.
Okay, tell me.
So for A, we can give 0, A1, A1.
Sorry, for A1 I give 0.
And for A2, we can give 101.
101?
Yes. And for A3, we can give 100.
Mhm.
And A4 we can give 1 1 1.
One more.
And A5 we can give 1 1 0 0. So A4 it's 1 1 1. A4 it's 1 1 1. Yeah, this can be generated by using frequencies.
And what are the frequencies? Yes, this can be generated by frequency.
Increasing order frequency. A1 frequency is more than A2
No,
more
but
than.
any increasing order does not help, right? Because okay, maybe set 10, 9, 8, 7, 6.
And the next one we can have 1 1 0
No,
1.
yeah. Means when if you are trying to prove a counter example,
Yeah,
try to
because
find a
here we
maximum
have
counter.
A2, A3, A4 as just three. The code has only weight of 3, so it is better than.
Correct, correct. Very good, very good. Excellent. Can someone, not the one who has spoken, can someone explain why this is the counter example?
Excuse me, sir.
Yes.
Sir, can't we just use like the binary representation of like 0 to n minus 1 for like a1 to an?
But that algorithm does not work. We already seen in this example. This is not the best approach.
Like in the third example, right, sir? Like
Oh,
we
okay,
can
this is
use
not a
0,
better
1 and 1, 0.
here 0 1 and 1 0. Yes,
Hmm.
but then
Even
still
then,
it is not this not the so you're saying if it is 1 0, then it is not a fixed length code, right? Then we are doing variable length code.
okay, okay.
Because in typical convention, ASCII coding and those things, those are fixed length code. That is the first one, blue one. So fixed length code obviously is not the best choice.
Sir,
Yes.
sir,
Can
in the
someone tell
counter
me why?
example,
Yes, this counter example, yeah.
sir, in the counter example, if we going towards the decreasing frequency,
Mhm.
the bit code length is also increasing. So at the end of the day, cost is, remains same, and we have a same problem.
So are you saying this is not a counter example?
No, this is a counter example,
Okay,
but
yeah.
our cost will eventually increase because when we think about to decrease the frequency, there might be the bit code length will increase.
We are not increasing or decreasing the frequencies. Frequencies are given as a input. Look at the problem definition. Frequencies are given as the input. Output is we need to decide what should be the code for each of the symbol. Am I missing anything? And here I am looking for a counter example. A counter example is a problem instance. That means an example of input where our algorithm fails. That is what we mean by counter example. Okay. Yeah. Anyone can someone tell me why, without forcing me to do the uh, tedious calculation, why this counter example sort of will work? If not with these numbers, um, or can someone help me why this one, the approach one, uh, is not a correct answer? Can you help me with counter example, or sort of push the idea of this counter example so that it is clear to everyone of us without doing this calculation that yes, this approach won't work.
So like in the previous one, the number of bits we were using for each of the like for each of the AIs were increasing with I.
Correct. Yeah.
And in
Very
this one, they're like for A2, A3, A4, they are same. So we can readjust the weights in such a way so that we can like get a lesser average value than the previous, like than
yeah.
case one.
Yes. To some extent, but can you give me an example where fixed length encoding works? The most easiest fixed length encoding is the optimal thing. Can you give me an example of it?
When there are only two things like A1 and
Or
A2.
yeah, when all the frequencies are same. If all the frequencies are same, then
Yes.
and assume that n is power of 2, then fixed length encoding is best. Because whatever encoding, assume n is 8 or 16 or any power of 2, large power of 2, say 64. Now whatever encoding you use, you need to use at least log of 64 base 2, which is what? Which is 6, at least 6 bits. Okay, so there will be some code words which will be at least 6-bit long, and if all the code frequencies are same, then it is sort of visible that fixed length encoding is the best. But now apply when apply the approach 1 on the input when all the frequencies are same and n is large, let n be large, then for lots of words from a log n to an, it is using extra bits. It is not using whatever bits it has used, and it is using so many extra bits, and the frequencies are same. Okay, so for example, let me for concreteness, say you want to say, I don't know, a very big number, 2 to the n. Now what is the, and their frequencies are same, they are all ones. These are all 1, these are frequencies. Now what does this for large enough n, what will be this cost? Cost will be like, what is the cost formula? This PA is 1 for everything. So it is the sum of the number of bits to encode it. So what is this cost? This cost is like 1 plus 2 plus dot up to 2 to the power n. Are you getting my point? Contrary to it, if I use simple fixed length coding, fixed length, then what will be the cost? Fixed length. There are 2 to the power
n square.
No, 2 to the power n many terms and log n. Which one is bigger? Obviously this one. Why obviously this one? First one is bigger than the second one.
So we know it by the formula of a geometric progression.
Yes, correct. So
It
this
would
is
be
this
2
is
to the power
exact.
n plus 1.
But this is not a geometric progression. This is a arithmetic progression. 1, 2, 3, 4. But I will let you prove. If you just do this arithmetic progression, yes, this is roughly 2 to the power 2n by arithmetic progression 2 to the power 2n. The sum of 1 to n is roughly n square, no? On the other hand, it is like the c prime is 2 to the power n times log n. The c is like 2 to the power n times 2 to the power n. Can everyone see why c is much larger than c prime? And understand the counter example? So this approach won't also work. Then I am running out of approaches. Tell me some other approach. And here is this crucial, another important point that, let me write here. That's where I kept the algorithm part blank. Is that first is, let me write this way in colloquial language, change perspective. What do you mean by that? Here, what is the output? The output is, this output is a table, and table is sort of it's very non-trivial to understand or tackle, messy. It does not have much structure. Do you see what I am saying? So, can we view the output in some equivalent format which has more structure, which has more, we know much more about those structures than table. If you have a table, what comes into your mind? It's just a boring list of numbers, isn't it? So the first step is change the approach, and let me write this way with color. View codes as binary tree. Why we are doing this? In the hope that, because binary trees has more structure, if we can view each code, by codes means that entire table, the entire output of this, not codes, let me write code only, or coding, view coding scheme, view coding, that means the table, view the table, coding or table as a binary string. If we are able to do that, then we have more structure, and tables, binary trees are much easier to sort of visualize and work with. There are parent-child relations and so on and so forth. So how do we view a table code with binary trees? And here is how. So let me copy one table and show you with an example. What do I mean by this? Viewing this table, duplicate here. Viewing this table equivalently as a binary tree. So it's a rooted binary tree, and the idea is whenever you have a 0, you should go left. So edges are labeled here. Okay, so edges are labeled and vertices are not labeled here, at least internal vertices. So the left edges are labeled with 0, and we start at root, this root. So from root, if you take the 0th edge or edge with label 0, what symbol you get? This is A. So whenever you got a symbol, you mark that node with that symbol. Okay. Okay, so 0, and then after 0 there is 1. So I mark this path 0 1 by the corresponding symbol, which is B, and C is 1 1. So this is 1, and this is also 1. So here is my equivalent view of this particular coding, this particular table as a binary tree. Let's take another example just to ensure that everyone have understood. Let me convert this also. Now you help me, please. Let me write A. How should I write A? Feel free to unmute and speak.
From
So
top
the same
go
will be
to-
noted for the first one.
Yes, same. Very good. So left one is A I have written. B is on the right, 1. And C is 0 1. So this is 0 1. Okay. So is this clear to everyone how this correspondence is done? How we are viewing tables equivalently as these binary trees, and this is a equivalence, means this is a bijection. Means it is given a table, you can draw the code tree. Let's call it code tree, or given a code tree, you can write a table. All nodes are not labeled. Some nodes are labeled, and the labels are exactly the symbols. Okay. feel free to unmute and speak if you feel you cannot do it, and I need to do one more example. Given a table, a code, given a code table, I can write a corresponding code tree. And given a code tree, what is a code tree? By definition, left edges are marked with 0, right edges are marked with 1, and some nodes are labeled with symbols, and they are the symbol of the alphabet. Other nodes are not labeled. Okay, very good. Now we must be able to reuse the knowledge or effort we have put in the table world. In the table world, we observed that the codes must be prefix free. So what do we mean by prefix free? Prefix free. What do you mean by prefix free codes in the code tree world? Can someone tell me what does that mean?
So there cannot be any labels in the middle of the tree.
Excellent, excellent. All internal nodes. Internal nodes means which are non-leaf nodes. All internal nodes are unlabeled. Thank you. Not exactly. Okay, so let me because if some leaf node is also unlabeled, then it is fine. So let me write let me not write this way.
So all terminal nodes are unlabeled. Non-terminal nodes.
What I meant is that the problem is that let me copy. The problem with this equivalence is that let me show you. Then you will be able to understand. Is that if there is another sort of terminal, there is another leaf node and it is just hanging, it is not labeled. So for example, and let's assume that this is not a label. So suppose this is a code tree. This is a code tree. Is this prefix free? Obviously, there are only two symbols, A and B. One is 0, another is 1. But that is not sort of matching with our definition that all internal nodes are unlabeled. Internal nodes are labeled here.
So, but in this tree, the additional nodes are redundant. So we would never even make it in the first place.
Can we formalize it? Can we more? So by redundancy, can we can we say redundancy or define redundancy in terms of code tree? What do you mean by redundancy or code tree?
So any branch which ends in an unlabeled node should be removed, maybe.
Yes.
Sir, no node has a parents node labeled.
Yes,
any parents node.
Non-redundancy. Yes, you are correct. Is equivalent to all leaf nodes are labeled. Are labeled. Can I say that? All leaf nodes are labeled. If some leaf node is not labeled, what that leaf node is doing? You can simply get rid of that leaf node, and the code remains same. For example, here, if we simply delete, we simply delete. For first, I delete this non-leaf node, this leaf node because it does not have a label, and reduce the redundancy, and I apply the same trick again. Then this is the same code. This shorter code tree, which has root and A and B, and it corresponds to the same code table, same code table. But now it is much easier object. It does not have any redundancy. Are you getting my point? So without loss of generality, we can assume that we will only work with code trees where all leaf nodes are labeled. If there is a leaf node which is not labeled with the symbol of the alphabet, why keep that leaf node? Delete that and make our life easier. Okay. So now from now on, in the definition of code tree, let's put this definition so that everyone's life is easy. That only leaf nodes, leaf nodes cannot be unlabeled. Leaf nodes must be labeled. So let me make this convention that leaf nodes must be labeled. Leaf nodes must be labeled. And we still have this equivalence between code tables and code trees, because those leaf nodes are unlabeled. Leaf nodes are simply hanging there without doing any work. Now, if I first make this convention, then this prefix free thing is fine. Then I can define, okay, a code is prefix free if and only if all internal nodes are unlabeled. Because if an internal node is labeled, through that internal node there is a leaf node also, and so there is a code whose code is prefix of another. You see, can you see now the equivalence? If there is any internal node which is labeled, then through that internal node in that subtree there must be at least one leaf node, and that is also labeled. So then then the code for that internal node becomes a prefix of the code for that leaf node. Prefix here simply means subpath, first part of the path. The codes are paths from root to that node. Anyone has any doubt here? Prefix free code means all internal nodes must be unlabeled. So what is the problem definition here in Huffman, for Huffman coding? Given a set of symbols, n symbols, alphabet, find a optimal code tree with minimum average depth of the labeled nodes, minimum average depth of the symbols. Because depth of the symbol, the length of the root to that symbol path is exactly the length of the of that code word. So our objective function is this C, which is a function of, say, let's call this a tree T. So for a tree T and a frequency of each symbol, this is for all symbols in the alphabet, PA times depth of A. Is this clear? I have just rewritten our original objective function in terms of these code trees. I want to design a greedy algorithm in this perspective, in this world where codes are code trees, and so the objective also I am viewing in this world, which is summation PA times depth of A. Anyone has any doubt why this is the equivalent objective? Simply because the depth of a node or which is labeled is the length of the code word, correct? Yeah, and we can say that depth of, we can actually write to something more, again to simplify, because we are only focusing on prefix free code. In the Huffman coding definition, it is must be prefix free. Then we know that all the symbols are there in the leaves only. So depth of the leaf node E. All leaf nodes are labeled, because if there is any leaf node which is unlabeled, then the tree is not the sort of smallest or most non-redundant tree. It has redundancy. Get rid of leaf nodes which are unlabeled. So all leaf nodes are labeled. But if we also insist that the code must be prefix free, then only leaf nodes will be labeled. Internal nodes cannot be labeled. Other than the code is not prefix free. So the depth of all leaf nodes, and each leaf node is marked with a symbol, and I am taking weighted average of weighted depth. So multiplying with question. Okay. Now, so even this view was also known when this Huffman discovered this algorithm, but still, you see that it's still not very clear. It's not very easy to come up with some greedy algorithm. So, in the interest of time, let me explain, tell you the algorithm. Once I tell you the algorithm, you will be convinced that yes, it is a greedy algorithm, in the sense that it is an iterative algorithm, and in every iteration we are taking some irrevocable decision, a myopic decision, which we will not change in later iterations. In that sense, this is a greedy algorithm. So, without giving formal definition, formally presented the algorithm, let me show the running of the algorithm with an example. I think that's the best one. So here are the symbols: A, B, C, D, E, F. And suppose these are the just writing some numbers. These are the frequencies. I've just taken some arbitrary set of symbols, 6 symbols, and the some frequencies. The algorithm builds this code tree in a bottom-up fashion. Now tell me which symbols must be very far from the root node. Is a greedy choice. Which symbols? Suppose I tell you, I give you a tree. I give you a code tree, the structure except the labels. That means there are leaves at various depths. Then what does what seems a good thing to do? Means which leaves will label with what symbols? So if you think,
the one with least frequency will go to the bottom.
Very good, thank you, excellent. The one with least frequency should go at the bottom. Okay, because that is the highest thing. That has the highest length. And this algorithm builds this tree in a bottom-up fashion. That's why it considers the node which is at the which will be the farthest. So it picks a smallest a symbol having smallest frequency, which is in this case F. And this symbol F, this will put at the farthest from the root. Can someone tell me, in an optimal code tree, suppose this is an optimal code tree. And this way, let me write the other way. So there are leaves at various levels. Here is a leaf here. At various depths, there are leaves. Okay. Okay, I know that the farthest one, suppose this is the farthest one, this will be labeled with F, the least frequency. Can someone tell me where will the um, the second farthest node will be? Second farthest leaf, where will it be? Okay, let me again ask the rephrase, not rephrase, let me ask the question. Suppose this is a chord tree and there is a farthest leaf node. This is marked with F. That I am fine. I'm trying to do a greedy algorithm. That I will mark F because that looks a greedy choice. Looks sort of the best thing to do with the current information I have, understanding I have of the problem. Okay. Next, let's ask where will the second most second most farthest from the root will be marked with what? Marked with the second one, the second least frequency, which is 2. C. The obvious greedy algorithm. The farthest one I will mark with the least frequent one. The second farthest one I will mark with second least one. Everyone convinced with me? Now, can someone help me with respect to the farthest one? Where will the second farthest one will be in that tree? In this optimal chord tree, which I still don't know. If I know the structure of the optimal chord tree, I will sort the leaf nodes according to the distance, and I'll just assign symbols to those symbols to those leaf nodes in that order. That will be the thing. So I don't know the structure also. If I know the structure, then I know which leaf node should be marked with what symbol. Okay, so here is an observation, a very crucial observation. The second farthest, the farthest and second farthest, let me use some other color. Suppose this is farthest and this is second farthest. The crucial observation is that they must be sibling. They must be sibling. Not only that, here is a very crucial observation which follows from whatever we have observed so far. All internal nodes in an optimal chord tree must have two children. Is the statement clear? If I look at any optimal chord tree, the leaf nodes doesn't have any children by definition, but the internal nodes, all internal nodes must have exactly two children. It cannot happen that there exists an internal node, but it has only one child. Why? And this is an observation. This is not a theorem or lemma, long proof. No, it's just observation. Okay, so I've drawn the picture of how an chord tree will look like if there is a internal node which have only one child. Can someone tell me why an optimal chord tree cannot look like this? It is prefix free, of course. All leaf nodes are labeled it is non-redundant in the sense that there is no leaf node which is not labeled. So leaf nodes are labeled, and exactly leaf nodes are labeled. Prefix free, so internal nodes are not labeled. But why? Yeah, please.
Sir, so it's not optimal because if we shift the shift some weight from the right arm to the left, we can traverse the tree in lesser time because the last
Very
layer would be.
good, very good. Thank you. What this nonsense, this single thing is doing? If it has only one child, so shift this child here, shift this entire subtree here. Is the picture clear? Delete this internal node which had only one child, and shift this thing. That means if I draw it more pictorially, if this was the root of this subtree, shift it, put this in this place. Now also it is a valid code tree. Internal nodes are not labeled, and everything is fine. Not only that, if it is if red node was a labeled node, that means it was a leaf node. So after shifting, it remains a leaf node. So if it is labeled before, it was labeled now, that's fine. If it was not a leaf node, internal node, it was not labeled before, and now also it is not labeled. So everything is fine. But what by shifting, what we have able to do is that there are many leaf nodes in this tree, at least one, possibly many, but and there the length of the path from root to those leaf nodes have reduced by 1, and so I have got another tree, another code tree whose cost is strictly less. So that's why the optimal code tree, it cannot have an internal node with only one child, because we can then short circuit, we can get rid of that internal node and do the same job. Is this thing clear? Okay. So now we know in the Huffman, let's come back to the design of Huffman coding algorithm. Now we know, now we can do some progress that, we know that the highest depth one will be labeled with F, and the second highest depth one will be labeled with C, and they will be sibling. Why they will be sibling? We will prove it. So here is a theorem. This we will prove using exchange lemma, that the highest depth leaf and the second highest depth leaf are siblings in an optimal code tree. And let me write the proof, because I have already told you the proof. Already done. Can someone prove it to me? I've already proved it, whatever I just told. Okay, don't worry. So let's
Sir,
put,
if they are not siblings, we can like shift the shift the one with the like largest depth upwards.
correct. Sort of that thing. So few things are clear. So if I look at a an optimal code tree, one thing is clear. So if I pick any node which is farthest from root, there is a optimal optimal code tree which marks this node with the smallest frequency symbol. Let's call it F. Just using this example. Why? Because for example, suppose there is this marked with something else, then you can exchange. So if this farthest node is not marked with F, then find where is F. So if F is somewhere here, we exchange F. F is somewhere here, that means this must be also a leaf node, and you exchange the symbol F here, and whatever symbol was there in the red node, you put in the Fs place, and this is where the exchange argument again coming into picture, that this will only make the tree, the cost less. It cannot increase the cost because F is the smallest, F has the smallest possible frequency. Everyone with me? Now see who is its sibling? Who is the sibling of red node? It must have a sibling. Why it must have a sibling? Why this red node must have a sibling? The theorem says that the farthest and second farthest, they must be siblings. But why? What goes wrong if the farthest does not have a sibling? Again, the answer is we have just discussed. Why the farthest must have a sibling? What goes wrong if it does not have a sibling? No, I can just simply come and just tell you the algorithm and prove the correctness. That will take me half an hour, and I can cover a lot of contents also. But that will not convey the main thing. What I want to teach here is the process of designing the algorithm. The name of the course, okay, it's called algorithm one, but this is the algorithm design and process. This process you must learn. Okay, so in that spirit, let me not tell you the answer. The answer is very easy. You will be able to tell me. What goes wrong if the farthest leaf does not have a sibling? Let me help you, but let me not answer directly. No, if I don't know, it's so obvious. It's if I give any hint, you get it. The answer is in the board. The answer is on the board. Answer is on the screen.
Sir, because all the internal nodes are two children, must have.
Exactly. If a leaf node, if the farthest leaf node does not have a sibling, then look at its parent. Well, what is its parent? Suppose this is the parent of the farthest one. It must also have it's an internal node parent. Now it is then it also must have a child. Otherwise, it will have one child. That's not allowed. But can this child have another child? No. Say this yellow child of this green child, green node. This yellow child can this child be a non-leaf node? If this blue node is a non-leaf node, then again if does not have a sibling. It's a sibling, but what do I mean here is that yes, these leaf nodes are siblings. Yeah, this yellow must be a leaf node also. Why yellow must be a leaf node?
Sir, because it is a second largest now, and
Exactly.
it has a sibling. So now there is
Exactly.
no node
Exactly.
to be a children of it.
Exactly. The distance of red and yellow nodes are same. And we have just said that the F is the farthest node, the red node is the farthest node. Now, if it is not a leaf node, then that means there exists something else below it. And that means there will be another node, another leaf node, which will be further than F. That's not what we have said. We started with the assumption that F is this red node is the farthest node. That's why yellow node must be a leaf node, and it must be a sibling. And now greedy makes sense, because we know, as I just mentioned some time ago, that if we know the structure of the tree, then labeling the leaf nodes with the symbols is trivial. Just label the farthest node with the least frequent symbol and so on. Now, can you see the progress? I know the farthest node. I do not know its parent. I don't know its structure. But what I know is that its sibling will be the second. Its sibling, whose depth is same as its depth, and hence it must be a second highest, which is a tie, second highest depth leaf node, and it will be marked with the second most frequent symbol. And I know this local structure. So what I do here is that, let me copy this. What I do here is that I keep everything else same, and let's make little bit of progress. Whatever we know that at the end of there is a optimal code tree where C and F are children, are siblings of each other. So sibling means that locally in the neighborhood, C and F should look like this, that C and F are sibling, they are leaf node, and there is a parent node. So what I do is that I delete these nodes, C and F, and I sort of introduce a new symbol for the parent of C and F to be a proxy for the symbol C and F. Let's call this symbol CF just for name. How many times this symbol will be used? What is the frequency? The frequency will be the sum of the frequencies. It's like how many times this node will be visited on an average to visit the leaf nodes. Now this C is visited 2 times and F is visited 1 times. That means this 3 times. Yeah. So this frequency I am defined it to be 3. And because I know the structure of this subtree, that C and F, they are farthest and they are connected with this parent, and I know that locally this is the right structure. That means that there will not be any node after below C or below F. That's why what we do is that I segregate this part, C and F part mentally, not actually, and sort of pretend that as if my symbol set given is this A, B, C, F. This is just the name of the symbol. It's not 2 symbols I'm fusing. It's not like that. It's just a name of the symbol. I am conveniently naming it CF. D, and their frequencies are 5, 4, 3, 7, 9. Now I am delightful. Why? Because I now have the same problem of Huffman coding, but on the smaller input. And so I can iterate the same process. The same process. What is the same process? Pick the least 2 frequent words and make them sibling. That's the process. So B CF, and below here it was C, it was F, and again introduce a thing and give it a name, say BCF, and segregate the subtree below BCF mentally, because I know that the optimal code tree, an optimal code tree will look below BCF like this. So that part I do not need to worry about. I have already got hold of an optimal subpart under BCF. I do not know what is above BCF and so on and so forth. But I know that under BCF this part will be exactly like this, so I don't need to touch it. So what is my reduced problem instance? A is 5, B and CF I am deleting. I have BCF. What will be its frequency? Please tell me.
7.
7. Very good. Now again, let's pick two least frequent one. If there are ties, you can break ties arbitrarily, doesn't matter. Convince yourself after this class. A, then BCF. And BCF, how does it look? Okay, BCF will be the child. BCF. So let me not write BCF. Let me expand BCF. BCF actually looks like here is B. Where is C? Where is F? Okay, let's call it ABCF. So I delete this. And now I have only 3 symbols. ABCF. This symbol has frequency how much? Please help me. What is the frequency of ABCF? How much?
12.
12. Very. Thank you. Then I again pick these two. I know that these two will be siblings. I do not know how this part will be connected to the subtree we have already generated. That's why I'm not connecting it. So I'm maintaining a forest in every iteration of the Huffman coding algorithm. We maintain a forest, a collection of trees, which I know that these are valid. Each of these tree will be a valid subtree of the final optimal code tree that we are building. This we delete, and now we have only 2. If it's only 2, it's only one way. So this is an optimal code tree. Question on the functioning of the algorithm. If I give you another example of say 10 symbols and 10 different frequencies, will you be able to construct or run this algorithm, Huffman coding, and construct a optimal code tree? If you feel you cannot, not writing the code. For writing the code, you have to worry about how will you store these forest, trees, data structures you have to worry about. But at least with pen and paper, the way I have done, this much you should be able to do. If you feel you cannot do, please unmute and speak. I'll repeat. I want all of you to be able to execute Huffman coding algorithm at least with pen and paper. And that is what algorithm design is. That is what we are doing it now, algorithm design. How to implement it? their data structures will help. What kind of data structure and so on. That is also very important. But that is not the focus of today's discussion. That's why I'm not going to performance analysis. If you do naive implementation, you will get something. You can do better data structure. For example, for this case, the base data structure will be heap, min heap. But let me not, I deliberately want you not to focus there. That's easy part. That's not difficult part. And anyway, we will do data structures in much more detail. I want you to focus really on the algorithm design process. So please unmute and speak if you still feel that you are not able to, you will not be able to run this Huffman coding algorithm on pen and paper and compute a optimal binary, optimal code tree.
Sir, can you repeat it once?
Yes,
possible?
this is what everything is possible. I'm here to teach you. Just a minute. Let me mute it. Yeah. Okay. So I'm given a list of symbols and a list of frequencies. What I do here is that I pick in every iteration. I pick the two okay. So maybe this way it is better. Initially, I see input the n symbols as a forest with n trees. Each tree is a singleton node. That's why I have drawn in this circular manner also. Now, in every iteration, what I do is that I pick two trees which has least weight and merge them. So, in the first iteration, C and F, these two trees which are singleton nodes have the least weight. I merge them. Merge them means what? Create a node and make one tree a left child, another tree is right child. Does not matter which one you make left, which one you make right. Doesn't matter. Your choice. And this shows that the optimal code tree will not be unique. Typically, most likely it is not unique because at every step you have the choice of making which one you make left child and which one you make right child, right subtree. Okay, so you delete these two trees C and F and merge these two trees and put that in your input. And what is the weight of this tree? Sum of the weights of the trees which you deleted. So 2 and 1 was there and now it is 3. Initially I had 6 trees, each were singleton nodes. Now I have 5 trees because I have deleted 2 trees and put 1 tree. I have merged 2 trees into 1. And I repeat this process, same thing. Again I pick two trees which has least weight and I merge them. So in every step you see that I am merging 2 trees. That's why in every step I am reducing the number of trees I have, and if I have n trees to begin with, after n minus 1 iterations I will have only 1 tree, and that is the output of the Huffman coding algorithm, which is this. Okay?
Yes, sir, got it. Thank you.
So now we have to prove its correctness, and correctness uses 2 parts. One is that exchange lemma, as I mentioned in the beginning of the course class. Where? Here. Exchange argument, and this exchange argument we have already used. What we need, what I will now prove is the induction. So by exchange argument, what we have proved? Let me see. We have proved this theorem. The highest depth leaf node and the second highest depth leaf node are the siblings in an optimal code tree. This is what we proved using exchange argument. Now we will prove that. So in particular, this particular theorem says that proves that there exists an optimal code tree where the least frequent and second least frequent symbols are the leaf nodes. Okay. Next, what will I prove is that, so just for concreteness, let me write it. Not for concreteness, let me write it this way. For any theorem or if you want to proving something, first step is write concretely what you want to prove. What are the assumptions? Where is the goal? Okay, so let A and B be to least frequent symbols. We have already proved that there exists a optimal subtree, optimal code tree where A and B are siblings. Using exchange argument, we have already proved it. What we will prove it now is that Huffman coding algorithm outputs the optimal, say call it sigma tree. What is sigma tree? It's just a code tree. I'm just writing it formally. That means the leaf nodes are labeled with sigma, symbols from sigma. That's it. Huffman algorithm outputs the optimal sigma tree among those which have A and B as siblings. Particular statement we will prove using induction, that this Huffman coding algorithm outputs the optimal sigma tree among those trees which has A and B as siblings. If I prove this, now if I combine this result with the earlier theorem that there exists a optimal sigma tree where A and B are sibling, then I conclude that the Huffman coding algorithm outputs an optimal code tree. Is this clear to everyone? If I prove this theorem, then I prove that Huffman coding algorithm outputs the optimal code tree. Because in this particular theorem, the search space that I am confining myself, that means among all sigma trees where A and B are siblings, I know that there exists an optimal subtree in that reduced search space due to the earlier theorem which we proved using exchange lemma. Okay, very good. Now this is a proof by induction. So we would induction on what? As the algorithm suggests, the number of symbols are decreasing. So induction on the number of symbols in. Okay. What will be the base case? N equal to 0, 1, 2. Which one should be the base case? Induction is also a mysterious thing. Be very careful. You will see, you will find lot of fallacies in inductive arguments. Although easy, very powerful, but if you're not careful, it will be, the proof will be wrong. What will be the base case? What should be my base case? 0. Most convenient. I don't have to prove anything. Can I is n equal to 0 as a base case okay for this proof?
Sir, like for n equals to 2, I think that will be best
Very
case
good.
case.
Very good. Very good. Can you explain why?
Sir, because if n equals to 2, then both the alphabets will be sibling.
Correct. In some sense, you see that for n 0 or 1, this statement is sort of does not make sense. For example, if for n equal to 1, 0 and 1, the statement does not make sense. What do you mean by there are two least frequent symbols? There is no two least frequent symbol if n equal to 0 or 1. So what are you proving by induction? The statement itself does not make sense. So the base case must be n equal to 2, the smallest value of n for which the statement makes sense. Now for n equal to 2, it is obvious because the only prefix free code prefix free code tree is this. There is no other option, and this is the one which the algorithm outputs. So n equal to 2, this is fine. Everyone is with me? For n equal to 2, it is fine.
Yes, sir.
Okay. Now you see that now inductive step. So suppose assume for n and assume for say 2, 3 up to say n minus 1, and we will prove it for n. Okay. So first is, suppose this is the output of the Huffman coding algorithm on this tree T on n nodes. What did the Huffman code in the first iteration? What did it do? It ensured, and this is T prime. Tell you what is T prime. So T prime is the tree constructed say after the first iteration. That means here we have n symbols here. Here we have n minus 1 symbols. Okay, and here there were one extra new symbol, which was what? By our convention, AB. So here it was AB. Okay, here it was AB. A new symbol was there. This symbol was not there in T. But what was there? How we construct T from T prime? It's just we expand this thing AB. If I look at the symbol AB, which is a leaf node, and I make it a non-leaf node with two children A and B. That's how the Huffman coding algorithm worked, isn't it? Okay. Now let me relate the cost of these two trees. What is the cost of T and what is the cost of T prime? Can someone tell me? What is, I need to write something. What should I write? How does cost of T and cost of T prime relate to each other?
Sir,
So
plus sum of the frequency of 2.
Sum of the, sorry?
Frequency of the 2 A and B.
Excellent, excellent. What is the cost? It is the, look at the leaf nodes in this tree, and it is those paths. All leaf nodes, the length of the paths have the same length, except for this leaf node AB, this was the path, and here was no AB. Two extra nodes are there, and their length was one more than the length of AB. And what is the frequency? What are the frequency added? PA added and PB added. But what was the frequency of AB? It was PA plus PB. That's why the term I should add is this plus PA plus PB. Because the length of A and B is one more than the length of AB, and that's and the contribution for these leaf nodes A and B is uh, is is PA plus PB more, because the weight of the leaf node AB was PA plus PB. Is this equivalence clear?
Yes, sir.
Now this equivalence does not depend on T prime. This holds for all T prime. In particular, the optimal one, optimal T prime, for optimal T prime also it will hold. So if I, and this holds for all T prime and all T. All T where A and B are siblings. And the mapping is also very clear. If I give you a code tree where A and B are sibling, then you can go to the T prime world and you construct a T prime, you just simply merge, fuse A and B. So this is an equivalence. This is a one-to-one relation. And this is a sort of a translation in the sense that their costs are related by constant, something not dependent on the process of how you are converting. So if T prime is the optimal code tree for this by induction hypothesis, T prime is the best code tree for this new symbol set, then it follows that T is also the optimal code tree for this symbol set, for these n symbols, and that's what concludes the proof. Okay, so it's very easy. That's why I always, I sincerely request you, I beg to you that proofs are not difficult. You first have a clear idea of the question. Think of, take your favorite subject, which you think you are very good at it. Now, if you don't look at the question and just start jumping, writing the answer, how horrible idea is that? Same thing with proof. The question is theorem statement. Clearly read, clearly understand what is given. What is given means is where you are, and what you need to prove. That means where you need to reach. Once you have clarity, complete understanding, proofs are often very easy. For most students, for most people who has difficulty in proving theoretical statement or any statement, proving means theoretical. There is I don't know of any proof which is non-theoretical or non-formal. So you clearly understand what is given and where you need to reach. It's like where you are and where you need to reach before taking the some path. Okay, question on the proof. Okay, you can think about it. I think it's a good time to take a 5 minutes break. Sorry, I did not want to stop in between, but now we should take a 5 minutes break. We have earned it, and we will come back. You can think of your questions. I'll come back at 11:46 in my screen time. Now it is 11:41. We will come back at 11:46. Thank you. TS, have you taken attendance? If you have not, please take. Okay. Questions on today's lecture? So let's come from beginning. Let's do a brief recap of today what we have done. We have done the second and last example of greedy algorithms, Huffman coding, and we have seen how changing the perspective helped us immensely to design the algorithm. Initially, we were trying to come up with an optimal code table, and table is sort of monotonous and less structureless, something like that. And then we saw that let's view the tables as code trees. And in the table world itself, we have observed few problems with the codes. Not all codes are desirable. We need the ability to uniquely decode the code, and that's why we come to the concept of prefix free. We observe that if a code is prefix free, then if a code is prefix free, then the decoding is unique in the sense that every binary string, which is a valid code word, has a unique unique string over the alphabet. But we left that with the question that but is the prefix free code word necessary? So definitely prefix free code word, a code being prefix free is a sufficient condition for uniqueness, but is it necessary? In the sense that can there exist a code which is not prefix free, but the decoding is unique? That means every binary string which is a valid code word, which is a valid code word, can be converted back to a unique string over the alphabet. Is it the case, or is the prefix free condition is a necessary condition? Yeah. Is it a necessary condition? So yeah. So let me comment here. We have seen that this is sufficient condition for unique decoding. Unique decoding, but is it a necessary condition? Is it necessary? The question below in blue color is basically asking that. We have seen that the algorithm is not even finding what are the possible greedy algorithms, that also not trivial. And in the code tree world, we once after viewing the code tables as code tree, we sort of exported all our findings in the code table world in the code tree world. That means for a code to be prefix free, it must be the case that if I take two nodes with labels, one node with a label should not come in the path of another node. That is what a prefix free code means. And always, we should always try to make our problems, our life easier, simpler, so that we have clarity and so on. We make our life easy. So that we also observe that many of the possible code trees are redundant. So we ensure that we only work with non-redundant code trees, in the sense that all leaf nodes must be labeled. And now, if all leaf nodes are labeled, we already see what this removal of redundancy, how it helps. It ensures, it makes the definition of prefix free very easy. All internal nodes must be unlabeled. So internal nodes must be unlabeled and leaf nodes must be labeled. That's it. And we further observed another structure of optimal code tree, the code tree which achieves minimum cost, is that every internal node must have 2 children. If not, then we can short circuit it. That's simple observation. Then towards designing a greedy algorithm, we sort of try to find out where can we have something, or for example in the in yesterday's class we sort of pruned other dimensions and sort of tried to understand the optimal algorithm with respect to its behavior with respect to one dimension, with respect to weights, with respect to lengths and so on. Here also we do not know the optimal algorithm, we do not know the optimal code tree, but still we are sort of studying or trying to understand what will be the structures. Are there some structures, some part of the optimal code tree which we can tell or we can construct now, and towards that journey, towards that using that approach, we observed that yes, we know, first of all we observe that if we know the structure without labels, then it is very easy. Simply label the farthest leaf with the least frequent one and so on. Keep doing this. So what is important is the structure, and we also now know with this observation that the farthest one is the least frequent one, must be labeled with least frequent label, least frequent symbol. Then we also observed that because of this observation, from this observation that internal nodes must have 2 children, the farthest one and the second farthest one, they must be at the same distance from the root node and they must be sibling. And so we know that the second farthest one, whose distance is the same one, there exists a second farthest one which is a sibling of the farthest one, and their labels also we know. Their labels are one label is the least frequent symbol and the second label is the second least frequent symbol, and they are siblings. That means in some local neighborhood I know the structure also. That means their parent is same. And with only this sort of information, which I sort of discovered by studying the structure of the optimal tree, we sort of designed our greedy algorithm, Huffman coding algorithm. And that's it. And then we finally proved that this Huffman coding algorithm always outputs an optimal code tree by proving that something simpler, because we have already proved that there exists an optimal code tree where the least 2 frequent symbols are siblings. So why not? Why reprove what we have already? Why reprove what we have already proved? Let's only prove what is remaining to be proved. That among all optimal subtrees in which the least 2 frequent symbols A and B are siblings, let me prove that Huffman code outputs one of the an optimal sigma tree among those class of sigma trees. So see always that you always try to be very clear about what we have already proved, what we need to prove, so that you can make this baby steps and focus. And see, once again we have understood clearly what we need to prove in the theorem, what is given, clearly write what is induction, then the proof is very easy, very easy. It's just connecting the costs, and that's what we want to prove. This cost is not something we have to think from out of blue. We want to show that the Huffman code works for n symbols. We have assumed that it works for n-1 symbols, and works for n symbol means what? The cost of the code tree for n symbols is the best possible. So what we know, we should always try to exploit what we know, what information we have. We know that for n-1 symbols it works. That means the cost of the code tree with n-1 symbols, that is the least one. So that sort of prompted me, guided me to relate the cost of these 2 trees. And once I relate, it is obvious. Question. So I am I am out of time. So I am here to answer your doubts, questions. Feel free to leave if you do not have any question or if you have any class or anything. Thursday we will see some exercises. We will do some exercises on greedy algorithms, and this Saturday, hopefully, we will do exercises on divide and conquer. So divide and conquer, although we have learned before, we are postponing it slightly. With that, we will probably do this Saturday. Thursday, we will do some more exercises on greedy algorithms. Questions? If you do not have any question and if you have any other class, feel free to leave. We will meet again on Thursday at 8 o'clock in the morning. Okay, so there is no more question. So